Hello, my name is Steve, and these are my team members. Wong Shen Yong, Zhu Zhengzi, Steven Ling Wei Seng. We are part of the team Konnichiwa. Together, we have conducted a detailed study on aquaculture automation systems, examining various technologies and the impact on the efficiency and sustainability of aquaculture operations. In my part, I will explain the background study we did on the key functions of automation systems and compare some of the most popular systems available in the industry today. So, for the first one, we have the common aquaculture automation functions. The first one is automated feeders. Automated feeders dispense feed at regular intervals, optimizing nutrition and reducing waste. These feeders use sensors and AI to adjust feeding based on fish type and conditions, improving growth rates and reducing labor costs. Up next, we have the water filtration system, recirculating aquaculture system, short for RAS. RAS technology recycles water by filtering out waste and controlling ammonia levels, promoting a clean environment with less water usage. This is essential for fish health, growth, and environmental sustainability. Next, we have the water quality monitoring. The water quality monitoring is automated water monitoring, uses sensors for continuous data on temperature, pH, and oxygen levels, allowing for quick adjustments. This real-time data minimizes labor and helps prevent harmful water conditions. Next, we have the oxygenation system. These systems maintain adequate oxygen in intensive farming environments to meet fish needs, compensating for insufficient nature oxygenation. This promotes healthy, thriving stock. Next, we have the temperature control system. The temperature control system stabilizes the water temperature, which is crucial for growth and health in aquaculture. Automated systems allow optimal temperature adjustment, improving feed efficiency and disease control. Next, we have the lighting system. The lighting system is just a automation which adjusts daylight hours, affecting fish growth and behavior. It has advanced LED systems which simulate natural light cycles for species-specific requirements, supporting growth and reproduction. Last, we have the alarm and alert system. The alarm system monitor key conditions, notifying farmers of critical issues such as low oxygen or high ammonia. Modern alarms use SMS and online dashboards to ensure quick and effective responses. Next, we have the most popular agriculture automation system. These are the systems on the market incorporated. Here are the examples. The first one is ABB Aquaculture Solutions. ABB integrates water quality monitoring, automated feeding, and energy management into a real-life system that improves productivity and cut costs. IoT sensors enable remote monitoring and precise control. Next, we have the repeat automation system. The repeat automation system specializes in feed production automation, ensuring high quality feed and supporting regulatory compliance, which reduces waste and labor while maintaining food safety and standards. And then the last one, we have the IoT-enabled aquaculture by Epicensor. Epicensor's IoT-based system tracks water quality, adjusts feeding schedules, and monitors fish health. It allows remote management and efficient operation, ensuring sustainable fish farming practices. And this is the comparison and contrast table for the three system above. For this, I will do a brief explanation for the table. The ABB Aquaculture Solution System excels in real-time water quality monitoring, IoT-based automated feeding, and energy management, focusing on the optimization part for the fish behavior monitoring and regulatory compliance. Whereas the repeat automation system is more specialized in feed production, prioritizing consistency, operational efficiency, and regulatory compliance, with less emphasis on direct health monitoring and energy management. For the epicenter, it's IoT-enabled aquaculture integrates IoT technology for continuous water quality monitoring, automated feeding adjustment, and remote management, providing a data-driven approach with an emphasis on reducing energy consumption and labor. Up next, we have the selected aquaculture functions that can exist as a self-contained system with three existing examples of products. First, we have the water quality monitoring system. This function continuously tracks pH, oxygen, and ammonia levels, which is essential for fish health and stability. Quick responses prevent stress and diseases, enhancing farm productivity. The example existing products are Senior Reef V6, Pro DSS multi-parameter water quality meter, Aqua Tro 500 multi-parameter sonde. Next, we have the feeding automation. The feeding it is a automated feeding schedule, optimize nutrition without overfeeding, improving growth and reducing waste. Timing and light sensors are used to precisely control the feed distribution. The existing products are Fishmate F14 Aquarium Fish Feeder, AHEM Everyday Fish Feeder, and the Hydra Wi-Fi Intelligent Fish Feeder. And then we have the oxygenation system. It maintains the optimal oxygen levels, which supports fish respiration and prevents hypoxia. This system includes dissolved oxygen sensors and pumps to keep stable oxygen levels. The existing products are Tetra Whisper Air Pump, Marina 50 Air Pump, and the Cobalt Aquatics DC USB rechargeable air pump. Next, we have the temperature control. The temperature control allows optimal growth and health for specific fish species by adjusting the water temperature, supporting reproduction and reducing disease risk. The products are Delta Star Heater S, Thin Aqua Temperature Controllers, and the Tegor TK Chillers. And last one will be the water level monitoring. The water level monitors prevent overflow and drying by ensuring tanks maintain consistent levels, which is essential for stable fish environments. Sensors and pumps manage water levels accurately. The existing products are E plus H, Prosonic FDU90, ultrasonic level sensor, ground force pumps, and the last one is Hydrogate overflow gate. And that is from me. Wong will be handling the part 2, which is the individual system logic design.
Thank you, Steve. I am Xiang. Now I will talk about individual system logic design. Firstly, there is water quality monitoring system. For the water quality monitoring, we're using 3 sensors. There's pH produce sensor, ammonia sensor, and nitrate sensor. For the pH, either the pH produce sensor is showing the high pH value or low pH value, or ammonia sensor showing the high value, or nitrate sensor showing the high value, they will trigger the alarm. If the pH value sensors are showing the high value and low value at the same time, it will trigger the error output to mention the user that the sensor is unusual. Secondly, there is the feeding automation function. We are using timer sensor and light sensor. Users can set the timer to trigger the feeding operations or set the light intensity to trigger the feeding. For example, when the timer sensor detect the time is time out, or the light sensor detect the light intensity is higher than the setting, they will on the motor to dispense food to the fish. Thirdly, there is the oxygenation system. We're using the dissolved oxygen sensors to generate the dissolved oxygens in the water. When the dissolved oxygen sensor is not detect the dissolved oxygens and the sensor is safely to detect, then they will on the air pump to pump the air inside the water. Thirdly, there is temperature control functions. We are using the temperature sensors to detect the water temperature. If the water temperature is lower, then they will open the heater. If the temperature sensors it detect the water is high temperature and the temperature sensor is no any error, then they will open the cooler to cooler the water. If the temperature sensors is showing low temperature and high temperatures at the same time, that means the temperatures sensor is got something wrong, something error, then they will trigger the error output and mentions the user can maintain or checking the sensor. If the temperature sensor is not sure anything for low temperature or high temperature, that means there are normal temperatures for the water. Finally, there is the water level monitoring functions. For the water level monitoring function, we're using water level sensors to detect the water level. If the water level is lower than the average, then they will open the water bun and water pipe to pump in the water inside. If the water level sensor is detected it is high water levels, that means the water is over, then they'll open the overflow gate to push out the extra water from the grass. That's all from me. Now I will pass my mic to the Stephen. Thank you.
Thanks, Steve and Yong. I'm Steven, and now I will introduce several key features of our system and how they provide greater control and flexibility to users through manual activations and deactivations mechanisms. First, let's look at the water quality monitoring systems. We have integrated a manual deactivate switch into our water quality monitoring system. This allows users to control the system's response to sensor monitoring pH levels, ammonia, and nitrate levels. When the system is activated, sensor continuously send data to logic gates, triggering warnings or alarms if the thresholds set are exceeded. When the system is deactivated, sensors are bypassed, stopping fault detections and alarm based on these parameters. This is especially useful during maintenance or temporary adjustments. Next is the feeding automations. Our feeding systems includes a manual switch to control the motor that dispenses food, primarily controlled by a timer and a light sensor. Using the switch, users can override automatic settings. When the system is deactivated, the motor won't run even if timer and light conditions are met. This allows precise control over the feeding schedules without altering timer or the sensor settings. Then there is the oxygenation systems. The oxygenation systems manual switch provides direct control over the air pump, which is typically operates based on dissolved oxygen levels and safety signals. When the system is deactivated, user can stop the air pump, even if oxygen levels are low or safety signals indicates a need. This enables manual interventions during maintenance or when automatic oxygenations should be paused. Next is the temperature control systems. A manual switch allows users to override the operation of heating and cooling components, which usually responds to temperature readings. When the system is deactivated, it prevents the heater and cooler from engaging regardless of sensor inputs. When the system is activated, the heater and cooler operate based on temperature sensor readings. This offers direct control during testing and maintenance. Now we have the water level monitoring. The water level monitoring systems includes a manual switch for managing water pumps, WAF, and overflow gates. When the system is deactivated, it stops automatic operations, preventing activation of these components. When the system is activated, systems functions normally based on sensor inputs. This helps quickly mitigate issues during maintenance or emergencies. Now, let's talk about the central control circuit. A crucial component of our system is the central control circuit, which features an 8-bit multiplexer. This multiplexer allows users to retrieve the status of actuators for each function by changing the input selectors. There's the S0, S1, and S2 here. By adjusting the inputs at the multiplexers, user can select which functions actuator status they wish to monitor. For instance, if a user wants to check the temperature control system, they can set the selectors accordingly to monitor the status of heater or cooler being on or off. And here is the truth table for selections inputs correspond to the functions. Additionally, the overall circuit diagram illustrates how the multiplexer integrates with the different system components, allowing seamless selections and monitoring. And here is the flow chart. In summary, these manual controls and the central control circuit give users direct control over key parts of the systems, enhancing flexibility and ensuring easy interventions during maintenance, testings, or adjustments. That's all for me. And now I will pass the mic to Zhengzi.
Hi, I'm Zhengzi. So this is the code of our monitoring system, which is using Python. So basically it consists of loops and if statements for each functions. So me as a user will key in the inputs detected from the sensors and the output will be observed to see whether the actuators are triggered or not. So let's get started. So the first one is the water quality monitoring function. And let's key in the input. So as you can see, the output is the alarm is triggered due to the high pH value and the high ammonia level. And if all the inputs are normal, then it will show the water quality is fine. And the second one is the feeding automation. So as you can see, if one of the input is yes, then the food dispenser will be triggered. And the third one is the oxygenation system. Okay, so as you can see, the dissolved oxygen level is fine due to the high oxygen level, but if the oxygen level is low and when it is safe to trigger air pump, then the air pump will be triggered. And let's go to the fourth, which is the temperature control. If it is high temperature, then the cooler will be triggered to decrease the temperature. While on the other hand, when the temperature is low, then the heater will be triggered to increase the temperature. And let's go to the next one, which is the last one, the water level monitoring. So when the water level is high, then the overflow gate is triggered. And when the water level is low, then the water pump and the water valve is triggered. That's all from our presentation. Thank you.